Okay, so hello. I'm Colin, this is Joel. We're sharing this talk slot today. So I'm going to tell you about some software for mapping experiments we've been developing at Diamond Light Source recently, and then Joel's going to tell you about some isosurface visualization tools that he's been writing. So what am I going to tell you about? I'm going to give you a quick overview of what Diamond is, mention what our Eclipse RCP products are that we work on, and then talk about the new developments we're doing for mapping experiments, which includes an element of auto-generation of the GUI and a new perspective for visualizing data with many dimensions. So what is Diamond Light Source? It's a synchrotron X-ray source, which produces very bright light, mostly in X-ray wavelengths, for a wide variety of science experiments. We've got about 30 or 40 operational experiments at the moment. It's the UK's largest single investment in science infrastructure in the last few decades, so it's quite a big thing. And it's largely government funded and free for academic use. This is what it looks like from the outside. It's a big donut building. And on the inside of that, you have a structure like this, where we have a ring around the outside. Electrons move around that ring. They get wiggled around and bent at bending magnets, and each of those positions, beams of light come off, and they're then filtered and focused in these arrays of hutches. There's often an optics hutch, which controls the beam, and then there's an experimental hutch where you do things with the X-rays, and then there's a control cabin where scientists sit with computers to actually run the whole thing. This is what it looks like inside. So you have a synchrotron ring with a whole lot of various magnets for focusing and bending, and at various points around this, beams come off and go out through vacuum tubes through the wall to the individual beamlines. This is an example of one of the beamlines. So see the beam comes in through a silver tube that's just behind the robotic arm on the right-hand side of the picture there. Comes to a sample position in the middle of the circular diffractometer. There's a couple of detectors that can be moved around to different positions. And there's also the robotic arm I pointed out and the sample carousel, so you can do automated sample handling and loading to try and maximize the use of the X-ray beam. So moving on to talk about our Eclipse RCP software. We produce two products at Diamond. One you've already heard about in Tracy's talk earlier, which is Dawn, which is a data analysis workbench. The other one is GDA, which is for data acquisition. So they share these modules in the middle. They both have Python and Python scripting environments. They can do data visualization and communication with external analysis tools. Dawn is then more specialized on the analysis side, so it's got many more functions for reading and converting data, handling metadata, and dealing with processing workflows and that kind of thing. Meanwhile, GDA is focused on data acquisition and running experiments, so this actually does communication with the hardware layer, and EPICS, which is our control system, which is effectively the drivers for all our motors. It's client-server architecture, so we have an RCP client, but also a plain Java process, which is the server. And GDA is responsible for a thing called the scan mechanism, which I'll explain next. So most experiments in GDA are based on the scan mechanism, and at its simplest, this just means take some parameter, which might be a motor position, it might be X-ray wavelength or the temperature of your sample, move it to a series of positions and record data at each point from any number of detectors. And you can then combine these 1D scans for multi-dimensional experiments. A particular case of those that we're working on now is called mapping, which is where you scan your X-ray beam across the surface of the sample, which means you have your sample on a XY stage and you just move it to different positions, record measurements, and you build up a map. It's usually done in a raster pattern, but it can also be done in spirals or random sampling. And we're finding an increasing number of experiments at Diamond need this, but there's some problems. Firstly, these are big scans. Quite often you'll do a two-dimensional map scan, but alongside that, you'll scan the X-ray wavelength. You might have a two-dimensional detector. You might rotate the sample and take a map at each point. So you can easily build up 4D, 5D, 6D data sets from these, which are pretty large, hard to handle. And it means you need new GUIs for both setting up the experiments to do those kind of scans and also for visualizing the results. The other problem we're facing, we've already got many bespoke GUIs in our software. And they're not actually even all using the same GUI technology. It's because historically we've been a fairly large team with lots of requests to deal with, and people have used whatever they think is appropriate for the task at hand, but it means that maintenance is becoming an increasing problem. So our solution to this, and what I'm going to talk to you about today, is a runtime dynamic auto-generation of the GUI. So this means that you reduce the maintenance requirements quite a lot. You're guaranteed to be up to date with your domain objects because the GUI is rendered from those at runtime every time they're needed. And it also has this benefit of fix once, fix everywhere, that if you make the GUI generator do the right thing, then it's guaranteed that that GUI element will always be correct whenever it's needed. So we've investigated a few options and decided to use an open source framework called MetaWidget. It's quite a powerful framework with a nice extensible architecture. It's focused on all sorts of GUI backends, so there's quite a lot of effort gone into their AngularJS and that kind of thing. So they've got a fairly basic implementation for SWT, but it is highly extensible. So we've actually added our own improved widget processor, which adds data binding for us. Just an example of what it can do. It can take a plain Java bean, no extra information whatsoever, and from that, it can generate, with a couple of lines of code, it can generate a GUI that looks like this. So a simple set of labels for each field and the appropriate widget for editing that field. You can get a much nicer GUI out of this by adding metadata. We've mostly been doing that by annotation so far, which is what you see in this example, but you can also do it from an XSD description if you have that. So you see we've got a few different types of annotations on here. That produces a slightly richer GUI. So now we've changed the order of those fields with the UI comes after annotations. We've made the name read-only, so you now can't edit that. We've put a minimum value of 0 on that example double field, so now it's invalid, it's highlighted red because we've put something negative. And we haven't actually made much use of this ourselves yet, but we've got this UI action annotation, which means we can actually auto-generate buttons which will call certain methods when they're pressed, and that could be quite powerful. How have we been doing this behind the scenes? We've been using an OSGi service to generate these GUIs. It's quite nice because it forces us to operate behind a clean interface. And within the GUI generation plugin, it's very easy to control the dependencies and make sure everything's satisfied. And it enforces this clean separation between the GUI generator and all the clients. And it means that actually we've been able to make this MetaWidget framework into a hidden detail of the implementation. Clients just pass a bean and a parent SWT composite, and they get back a composite widget, and they don't know about MetaWidget, the framework we're using behind the scenes. Other advantages of this scheme, the behavior is just added automatically as the GUI is created, and that can be data binding, validation, any decorators to add a richer behavior to your widgets. And you can also drop in complex widgets for specific typed objects if you want to. You can override the default auto-generation with more complex behavior. So this is now showing in the proper context. This is the GUI that is a work in progress now, but for setting up new mapping experiments. The main requirement of this was to have a simple setup GUI with all of the parameters you might need to adjust on one page and easily accessible without having to click through multiple pages as we had to on the previous version of the GUI. So we've got a bespoke top-level GUI here, but all of these individual panels for different objects are auto-generated at runtime from the correct object for that experiment, which means you change the parameters completely if you need to. And this is what it looks like in the context of the GDA client. So we've now got, that's the same panel I just showed you, but this is now in the context of a data collection with various data sets already collected, and the plotting system showing you some existing data at different scales and some underlying data behind one of those points. And actually, I'll do a live demo showing you this in Dawn as well. So now some demonstrations. I'm going to show you a video of it in action in GDA. It's hard to do that as a live demo because we need a server and some dummy hardware. And then I'll show you a live demo in Dawn. So this is the GDA in action. So I'm just starting a scan running from this rectangular region on here, so we're going to fill that in at slightly higher resolution. You can see up here we've got our auto-generated GUI for the region shape, and within that you can put different types of scan paths, which might be a grid or a spiral. Each one comes with its correct parameters because we've auto-generated the GUI when we need it. We've got full data binding, so I'm dragging on there, and you can see the updated fields on here. There'll be another example of that later. I can also type values in here, and it updates on the plot. I can change the different types, so I can draw a line on. You see the fields all update nicely. Line has different types of paths applicable. Two-dimensional paths don't work, but you can do one-dimensional ones. You can also select to do a single point. At that point, you can't do a different path, so there's no option there at all. That's a blank GUI. And we can do circles. And again, you see the data binding works nicely. The parameters update smoothly when you change anything on the plot. So that scan's finished. So you see here, we turn off that block of data, and then we'll turn it on again, and you see that's been filled in at much higher resolution. Now we're going to zoom in and have a look. I can click around that data, so behind each of those pixels is a two-dimensional data block, which is what came out of the detector. And let's say we're interested in another feature we found just here, so I draw a box around that, start another scan running, and that's now going to fill in that area. Just flap out these panels to show you we've got a different set of metadata about the sample here and some beamline configuration parameters. So this is where, at the start of an experiment, you would move those various motors to the correct points, and then you run your scan. So while that's running, I'll just explain what's going on in the background here. The GDA server is actually moving some simulated motors to each of these X and Y positions in turn. At each point, it's triggering our simulated detector to record a 2D data block. And that 2D data block is what you see in the lower plot there, and in the upper plot you see just a single summary value, which is what builds up your map. So I'll just wait for that scan to finish. And then hopefully we'll see some high resolution data filling in that gap. So now I'll zoom in, and now we've got better data. And so you see in a scientific context, this is potentially quite valuable. You can find areas of interest on your sample, and you can zoom in and get much finer detail about the areas you care about. And now I'll just show you some this is now in its context inside Dawn. So this is the visualization package, the data analysis package. So here's the main map. I can click around this and it'll show me the data underlying each point. Which in this case, for a dummy detector, we've got generating the Mandelbrot set as the main item, and then a Julia set behind each point. With an earlier version of the detector, I recorded some points with a 1D data block behind, so this will happily handle 2D data behind, but also 1D. So this now has lines. And actually, I can click on several points, and it will overlay the lines for different points while showing me where they were, which is actually quite powerful as well for comparison. And going back here, I've taken some higher resolution data with the two-dimensional backing. Firstly, you can see if I look at a single point, you get the single set, but again, I can compare 2D data sets. If I just click on points in a row, then they fill in like that. You can see them side by side. So again, it's potentially very powerful for certain types of experiments. And you can see here I've done some really high resolution mapping, so you zoom in and we've got data underlying this, and we can really zoom right in on this. So back to the talk. What are we going to do next? The future of this is still a work in progress. It's still not ready to be rolled out to the live beamlines. So first thing we need is more complex widgets for the auto generation. Key requirement we can't handle at the moment is collections. If you have a field in the beam that's a collection, then at the moment we just render nothing in the GUI, but when you want to be able to do a table or a list viewer, which is why I was interested to see Jay's talk about the NAT tables. We might have to have a look at that as a possibility. We also want to be able to do motor positioners, so if we get one of our typed motor objects which we know about, then rather than just giving you a simple GUI for that, it can give you a motor positioner which will tell you the current position, a demand position, let you move the motor around. We want to be able to do MJPEG streams from cameras, so if you pass in a beam with a URL containing an MJPEG stream, then it will render a full plot showing you that live stream. And we're also wondering about a periodic table widget to let you select elements from the periodic table. The other thing we need is, in relation to that fix once, fix everywhere thing, we need to get the GUI generation under proper testing. So we're thinking about automated testing schemes for that. We already have Squish testing for Dawn, but not for GDA at the moment, so we might use Squish, or we're thinking about giving SWT-bot a try as well. And the other thing, which I didn't put on the slide, of course, is we actually have to finish this work and roll it out to the beamline so the scientists can start getting the benefits. And that's the end of my talk, and I'll hand over to Joel. I'll take questions at the end of Joel's talk as well. Yeah, I'll just check in my pocket.
Hey, I'm Joel. I'm currently a placement student up at Diamond. I'm just working there for a year. I've been there for about 4 months. And essentially, I'm currently writing an Isosurface visualization tool for Dawn. And I'm basically just going to give you a quick demonstration of what it's capable of. Today, I'm going to give a brief explanation of the Isosurface plugin. I'm not going to go into much detail because I don't have much time and I could talk for hours about it. I'm mainly going to give you a live demonstration and then I'm going to talk about the limitations and the solutions of what Dawn provides and then hopefully talk about the future plans of the project. So what is an Isosurface? Essentially, the best way to describe it is it's a three-dimensional contour of a three-dimensional data set. It's a way of representing a single value within a three-dimensional data set. So for example, with this CT scan, you get a layer of images, and I can essentially render that into a three-dimensional shape. So basically, it runs on 2 plugins. I have the Isosurface plugin, the GRFX plugin. I'm not going to go into great detail, hence the undetailed image. But basically, I try to keep everything modular. So the Isosurface deals with the algorithm generating the service data through the marching cubes algorithm. It will send this data through the plotting service into JavaFX, which acts like the view, and then basically generates the triangular mesh for JavaFX, and then plots it. So yeah, basically the Isosurface plugin contains the GUI for the user to use. I have added some aspects to the JavaFX plugin, like scaling and such. It executes the marching cubes algorithm to generate the mesh, and then outputs service data via the trace system. The JavaFX plugin basically acts as a view, as I've said, accepts the service data and generates a mesh, and then basically just handles things like scaling, rotation, and positioning, as well as generating the x-axis. So the marching cubes algorithm is a huge part of this the Surface plugin. And basically, I'm sure many of you understand how the marching cube algorithm works, but for those who don't, essentially it creates an abstract cube that runs through the data set. And depending on whether or not the vertex values are true or false to the value you've selected, it will generate an 8-bit value and then compare this to a pre-generated a table of, triangular meshes, and then basically combine this into a singular model. You can increase the cube size, which will lower the resolution, or you can decrease the cube size and increase the time it takes to process the algorithm, but it will increase the resolution. Right, I'm going to give you a demonstration. This is just in case I can't get a demonstration working. I'll close this. Where is it? Okay, so. Oh, fantastic. It's being very slow. Sorry, guys. OK, so here we have a simple, what is actually a CT, X-ray CT scan of a fossilized lizard within a rock, but for some reason it's not coming up with, I'll just show you the other version. So essentially, as you can see here, it is a couple thousand images of this rock, and if you look here, you can see there's a slight bright spot, which actually relates to the lizard skeleton. But currently, this is quite hard to visualize in 2 dimensions, so the easiest way to do this is to create an Isosurface. Hopefully, it will run nice and smoothly, but for some reason, the laptop's being extremely slow. Sorry, guys. It was running perfectly smoothly yesterday. I think it's because it's plugged in, it's recording the data. OK, so this is basically just the start of the Isosurfaces. Oh, wow, it's really slow. So basically, if I just add a quick, the GUI is currently under development, so it may not look nice. So if I just currently add a quick surface, let's change the color to green because it's a lizard. The resolution's really bad. Let's make it opaque. And as you can see, we have a badly rendered, really low resolution lizard. So what we can do is quickly just change the name to lizard. And we can increase the cube size. I'm not going to go crazy high, crazy low, because the laptop is currently running quite slowly, but I should hopefully be able to give you a nice lizard from that stack of images. It's running horrendously slow. Yeah, really slow. I'm not going to be able to show you that on the data. I don't know either. It normally doesn't run this slow. Normally this takes about half a second to render, but for some reason it's not.
So do you also put lizards in the beamline?
Yeah. Oh, yeah, well, that's how we get fossilized skeletons. OK, well, that's just not rendering. I'll just leave that. And of course, right, it's going to take too long to render these, so I'll just show you some quick pre-rendered images. Because that's going to take way too long. Okay, well, normally what happens is I have this image stack, as you can see, and then basically you get a two-dimensional lizard that looks like this. Sorry, I couldn't show you in a live demonstration. If anybody wants to come up afterwards and I can show you when it's been unplugged from the system and stuff where it runs quite smoothly. I did the same thing with a skull, and as you can see, I've added transparency and the ability to render multiple layered isosurfaces, as well as you can see on the right, there is some axes involved, which are rendered in GRFX. But the big problem with Diamond is Diamond handles humongous data sets, potentially larger than a terabyte. I've spoken to many scientists who say some of their individual data sets are larger than a terabyte, and to render this through the marching cubes algorithm will be basically impossible because you cannot hold that in memory. But luckily for me, Dawn has the lazy data set, and essentially it works by pulling a subsection of the data from your hard drive or from the drive, from the storage basically, and then basically only runs the algorithm on that individual slice. So there's no need to downsample data sets in order to do this. Essentially, it works like this. You have a large data set, something like 25 gigabytes, and it will take us 2 individual slices, which could equate to 25 megabytes, and then runs the algorithm on those 2 slices. So I'll only need, in this example, around 50 megabytes worth of memory. I was going to show you this in action of a 25 gigabyte data set, but obviously right now the Isosurface thing is not running smoothly. So future plans. Optimization is a large thing. The marching cubes algorithm right now is not very well optimized, and I think that's the cause of making it quite slow. It's probably draining the CPU as well as the graphics card. Two-dimensional image slices. So anyone who's used a Viso is probably quite familiar with chucking a nice image slice onto your 3-dimensional render and then looking at it. Non-planar slicing, so being able to slice the image and cull data and various things like that, as well as handling 4-dimensional, 5-dimensional data. Right, I'd just like to remind you to just evaluate the session. Just give me a +1 or a -1 as you feel. Colin as well. If I've done badly, don't be mean to Colin. So yeah, I'd just like to thank Matt Gehring and Christina. I know they're not here, but if they listen. For basically, Christina built the prototype that I'm working on, and Matt Gehring has basically helped me out through the process, as well as Mark Basham, who's basically been helping me out as well. And basically, all the developers up at Diamond who've basically been really helpful. So yes, thank you for listening. Any questions? Honestly, and also, if anybody does want to go see the Isosurface running, actually running real time,